Yeah, totally.
Okay. All right, good. So let me begin to record. So at least.
This meeting is being recorded.
Okay, everybody, good evening. Good to see you. It's Thursday, April 15. Today was going to be the tax day, but I think they postponed it by 1 week. I was saying, what's peculiar with April 15? Okay. Yeah, somebody was going to ask me a question. Who's that?
Yeah, this is William.
William. How are you, William?
I'm doing well. How are you?
Okay.
Okay, so on the textbook on page 61, I just had a question about the table that we see on page 61.
Okay.
I understand what you were explaining last class about BIC and AIC.
Yeah, can you give me a second? Let me go there, okay? I have it on my other computer. Yeah, I have a table 2. Everybody, this is table 2.1 that I showed in class last Tuesday. Yes, William, go on.
Okay, so I understand that for the AR model in general, you test at the 5% level of significance, but I'm confused about how they tested the PACF and how they came up with P equals 3 and 9. And I'm referring to the first paragraph here that starts with as an example.
Oh, so as an example, so that's what you're referring to, right? As an example, consider the monthly simple returns. Simple returns is percentage returns of CRISP. Okay, Chicago returns in security prices. We have it at Baruch, value weighted index from table 2.1 gives the first 12 lags of sample PSC. Therefore, we identify an AR3 or AR9 for the data. That is P equals 3. The lag equals,
that's my question.
Okay, the lag equals 3. Okay, give me a second. All right, with the PACF, we identify, okay, the asymptotic standard error of the sample PACF is approximately 0.03. Therefore, using the 5% significance level, we identify, okay, what it means, William, is this. Suppose I were to show you, suppose I were to draw the, you see those PACFs, right, on the first line, right?
Yeah.
Suppose I were to draw it as a graph, yes?
Mm-hmm.
And on that graph, I put the confidence line up and down, the dashed line, right?
Yeah.
Then the PACF, the partial autocorrelation at lag 3 and lag 9 will break through the confidence band.
Right.
That's what it means. But how do you determine it? You see this where it says the standard error. The standard error of the sample PACF is approximately 0.032. If you divide each of the PACFs by 0.032, do you have your cell phone there? Can you do that?
Sure.
So in essentially what they are telling you is the T statistic is larger than the critical T. So yeah, so divide for PACF at lag P equals 3 is negative 0.102, right?
Yep.
Okay, divide that by 0.032. What do you get?
Negative 3.1875.
Okay, so that's larger than 1.96.
Oh, okay.
Okay, now let's go to
negative 1.96, right?
Yes.
Yeah.
So let's go to lag 4. Do the same for lag 4 or lag 5 or lag 6 and see what answer you get. Just for either 4, 5, 6.
So for number 4, when you divide it, it's 1.03, which is less than 1.96.
Which is less. So that's what they mean.
Oh, okay, okay.
Okay, so yeah, so this textbook takes some liberty with us because it assumes we know from statistics, but that's what it's doing.
Okay.
Okay, good. That's a great question. But it's always easier, when we do the R session with PACF, we draw the line, we draw the graph itself, and then we eyeball and see. at which lag does the line break through. So for this one, the PACF will break through in lag 3 and lag 9.
Okay, I got that. All right, thank you, Professor.
All right, awesome. I like those kinds of questions. Okay, thank you. All right, any other questions?
Professor?
Yes, Alec.
How are you doing?
I'm doing
So
okay.
based on your experience, which would you say it's the function that yields the best results? I know the book doesn't say anything, but what do you say between PACF, AIC, and BIC?
You mean, okay. Before I answer your question,
Okay.
good to
No
see
problem.
you too, my man. Yeah. So before I answer your question, let me make a general statement. AIC and BIC, oh my God, we use them for everything in econometrics, in time series, or particularly in econometrics. So here we're using AIC and BIC to determine which is the best lag, right? Are you with me? In other words, if we are kind of debating whether, like William just asked me, is this an AR3 model or is this an AR9 model? Because there's some confusion here, right? Because the two lines for PACF, they break through at lag 3 and lag 9. Are you with me so far?
Yes.
And we're not sure if this is an AR3 or AR9. Okay, no sweat. Time series says no sweat. We can use AIC or BIC to determine, to nail it down, to say, this is AR3 or this is AR9. How? If we're using AIC, a KK information criterion, then we shall see which model, AR3, gives us the minimum AIC value. Is it AR3 or is it AR9? Are you with me so far?
Yes.
Okay. If we use BIC, the same thing. We're looking for which model gives us the smallest BIC. Is it an AR3 model or an AR9 model? And that is how we nail it. Are you with me?
Yes.
Okay. Now, the same thing. When we want to do nonlinear stochastic processes for VAR, and we have two equations that represent nonlinear stochastic process for VAR, nonlinear stochastic, but we're not sure which equation is better. Are you with me? We run AIC or we run BIC. If we're using only AIC, then whichever model gives us the smallest AIC is the best model for that thing. So we're on table 2.1, we're using it on just for PACF, but we can use it for anything in statistics. Are you with me? To choose between 2 or 3 equations that doesn't even relate to what we're doing in this class. So AIC and BIC, they are really very general. Again, let me tap into your knowledge of ECHO 4000. It's like using R squared. If I'm doing y equals a plus bx, simple OLS, I can use R squared. If I'm using y equals a plus b1 plus b2, b1x plus b2x, multiple linear regression of 2 x's, I can use adjusted R squared. If I'm doing multiple linear regression of 10 x's, I can use adjusted R squared, okay? So adjusted R squared is what I use to tell me how good the multiple regression model is. The same thing, AR1, AIC is what I use to choose for whatever model I'm working with. Okay, which one is the best one? If I'm kind of debating which one is the best one. All right. So if you're asking me which one with AIC or BIC, which one is the best one to use, better one to use? Is that your question?
Yes, that was my question.
Yes. Okay. So for particularly for AIC, particularly for PACF, which one is the better one to use, AIC or BIC? We are not in agreement. in econometrics. We're not in agreement about which one is better, okay? But what I can tell you is that the BIC is more strict than the AIC, okay?
Yes.
It's more strict in the sense that it penalizes us more. For the penalty is much harsher for adding more lags.
More lags, yeah. Got it.
And that's why in the literature, guess what? Most people tend to use AIC over BIC, okay? Because they are saying, oh, to heck with this, too strict. It's like two professors. One is too strict, the other one is not so strict. The same class. I go to the one that is not so strict. To heck with the other one that is very strict. So roughly, that's what I'm trying to say. So if you actually read finance, what professors write, publish in finance, most of us use AIC. Okay, but me, for example, if I do my own research, before I publish it to the public, I send it for publication. I actually run AIC, BIC, Hanan, Queen. There are 4 I use. And then finally, I report only AIC. But in the literature, mostly you will see people reporting AIC. If they had to choose one, they choose AIC because that's the one that assigns the least penalty. So there your results, you have more leeway in achieving whatever hypothesis you're testing. Okay? I don't know if that answered your question.
Yes,
Yeah,
it makes a lot of sense.
Okay,
thank you.
That's
Professor, I kind of have a follow-up question.
It's really exciting, these things you guys are asking me. Yes, Roxolana.
So what would you use AIC for? To determine whether it's like an AR3 or AR9
Yes.
model?
Yes.
So why can't we just use PACF? Why can't we just see how many lags it breaks through, like visually?
Okay, so suppose I come to you, Roxolana, and everybody in the class. I say, look, you guys, do you know what I did all weekend long? You say, what, Professor? I say, look, all weekend long, I didn't sleep. What I did was I went to the New York Stock Exchange, and for each stock listed on the New York Stock Exchange, I downloaded 50 years of daily, the crazy stuff. I downloaded 50 years of daily data, and for each of the 500 stocks in S&P 500, I tested them, and bingo, look at that thing called Facebook or whatever, wherever, or IBM. Look, IBM is exactly AR3. Okay, I make that statement. Okay, I mean, I swear, it is exactly AR3 because I simulated an AR3 model. I simulated numbers from AR3 and I compared them to IBM. Bingo, they're all the same, exactly. So therefore, IBM is AR3, and I give it to you. I give it to Tulema, all of you in the class, right? I say, okay, guys, run the ACF function for me, the autocorrelation function for me, okay? You guys, you do it very nicely. And what do you see? Bingo, perfect, okay? Exponential declining, okay? So everybody agrees it's an auto regression model. So, but hey, Professor, you told us it's an AR3. So how can we visually confirm that, Roxolana? What do? You run PACF. Are you with me?
Yep.
Okay. And bingo, all of you say, oh, Professor, look, at lag 3, it breaks through. That line breaks through at lag 3. And then William comes and Danny comes and they say, but Professor, you didn't look further down. I say, why? Stop bugging me, guys. They say, no, Professor, let's look further down. It also breaks through a little bit at lag 9. You see what I'm saying? Oh my God. But I have simulated the numbers and I see that IBM daily return is exactly an AR3. Okay, and then I'm saying, oh my God, it's the end of life, it's the end of life. And then Alex said, hey, but Professor, hold on. Professor, but didn't you tell us that we can, it's okay if we are unsure between AR3 and AR9. Professor, you seem to be very, very sure it's AR3. But, you know, Danny pointed out breakthrough at lag 9. So Alec is telling us, why don't we run AIC model on that PACF at each lag, and let us see, because that will kind of help us nail it down. You see what I'm saying?
Yeah, so it's more of like a statistically proving that.
Exactly. So it's a statistical nailing down of our conclusion, whether it's AR3 or AR9.
Okay, thank you.
I'm sorry, I went all over the place to explain it. But I'm sorry, but that's really how to think about it, okay? So you eyeball the ACF, okay, it looks like an AR model. You eyeball the PACF, bingo, it's exactly AR3, so you're done. But if you eyeball this PACF and it's AR breaks through at lag 3, but further down breaks through at lag 9 or lag 12, but instead of doubting yourself, you say, okay, fine. Let's apply AIC. And the one lag 3 or lag 9 that has the smallest AIC is a true model. Okay?
Yep, sounds good. Thank you.
Okay. Any more questions? All right. Okay, so good evening, everybody. What I want to talk about tonight is, again, non-technical, but I want you guys to please just come with me, okay? Next week, we'll begin to do technical stuff, but I want you to try to understand why we're doing, why one of the reasons that we might be doing what we'll be doing next week. We already talked about the concept of stationarity. Is Danny here today? Yeah, Danny, you're here, okay. We already talked about the concept of stationarity. And I asked for Danny because he and I talked sometime away from class, after class, he had a question. And I was kind of trying to explain about stationarity. In your book, at the beginning of chapter 2 in your book, we introduce the concept of stationarity. And we say that it's a series, a time series is stationary if it has, by the way, remember, it's weak stationarity, right? In this class, we're dealing only with weak stationarity. That a time series is weakly stationary and therefore stationary if the mean of the series is finite, constant. What is finite? Finite means it's not a crazy number. It's not like 1 billion, 0.5. In fact, 1 billion is even finite, but it's not some crazily large, outrageous number. It is finite and constant over time. Okay, that's one. Secondly, the variance is finite and constant. Those are the two conditions for stationarity. But we also notice that a time series that is stationary, there's a very important feature of its autocovariance and autocorrelation. We notice that if a time series is stationary in the sense of weak stationarity that I described, saying that the mean of the series is finite and constant, and the variance of the series is finite and constant. We notice that for such stationary time series, that the autocorrelations among observations are different lags. If you have daily data, then between day 1 and 2, between day 2 and 3, between day 3 and 4, between day 100 and 101, that is time period separated by 1 lag. Anywhere in the series, if you calculate the autocovariance, it's constant. It's the same number is the same value for observations separated by 1 lag. You say, fine, let us calculate the autocovariance between the different observations, daily observations, instead of for one lag, let's calculate it for 5 lags. In other words, today, 5 days from now, 10 days from now, so 5 lags. We calculate autocovariances for observations separated by 5 lags, the same number. But that number is different from the one for one lag. The 5 lag autocovariance is different for the 1 lag. But the 5 lag is the same through the series. Statistically the same, yes. Absolutely. You guys are just brilliant. Because thank you. Because the numbers might not be the same, but then we test the hypothesis. Remember that? And we test each one to see if they are really the same or not, they are not the same. Okay. I mean statistically, that's what I mean. Okay. All right. So we notice that the autocovariances are separated by different lags are the same. Okay. Those ones separated by 1 lag, the same. Those ones separated by 5 lags, the same. Lag 1 and lag 5 might be different numbers, but as long as the observations are separated by 1 lag, they're the same. Okay. All right. So we therefore, when we want to define weak stationarity, we therefore say that those are the conditions that are important for weak stationarity: constant mean, constant variance, and then autocovariance that depends only on the lag length. Only, it doesn't depend on time. Okay, for example, what does that mean? For example, daily returns between in IBM returns in January 1 of 2010 and January 2 of 2010. If the autocovariance depended on time, then if you take autocovariance 1 lag at 2010 and take autocovariance 1 lag at 2015, they will be different. Same 1 lag, they will be different if the autocovariance depended on time. But for stationarity, it doesn't depend on time. It doesn't matter where in the time series you take those 2 observations. As long as they are separated by 1 lag, 1 day difference between them, it doesn't matter where if you have 50 years of daily data, it doesn't matter where you take the lag, either at the beginning 50 years ago, in the middle 25 years ago, or now. As long as they are separated by, as long as those daily returns are separated by 1 lag, they will be the same number. That's what we mean, that the autocovariance between observations separated by the same lag, that autocovariance number doesn't depend on time, it depends on the lag. So we define stationarity like that. It's technical. I mean, it drives you crazy to think about it in statistical terms, but that's what statisticians and econometricians tell us. Now let's come to real life, and what does it mean? So I want to spend a few minutes tonight, just you and I talking as if we're having coffee next to Baruch College, okay? After in between classes. Why is stationarity important? I mean, it's just one of those things that are so important because in real life, okay, if a time series like GDP, let's say GDP, if it is stationary, it means that thank you, Andrew. That means if you take GDP of United States from 1900, let's say annual GDP for now, to keep it simple, annual GDP of United States from 1900. Every year you look at the GDP, from 1900 to 2021. That number we say is stationary, okay? If we calculate the mean, first moment, and we calculate the variance and therefore standard deviation, second moment, if that series, if that GDP is stationary, then the average GDP of United States and the volatility of GDP will be constant. What is the first conclusion we can make? Number one, it's a normal distribution. The distribution is normal. You agree with me? Because if we say it's okay, I think that's a stretch. I just made a long stretch. If it's constant, I'm saying that we're looking at only the first two moments. Okay, okay. Let's just forget for now the fact it's normal, because I have to say other things. Okay, but if it's stationary, that means on average GDP in the United States is constant and the volatility is constant. Now, if, let me not say categorically it is, if the distribution of GDP is normal, I'm just bringing it in, then that means that that bell curve would be the same average and the same shape through time of GDP. I mean, wow, if you're the president of the United States, it's like, wow. That means or you are the minister, you are the head of the SEC or the whatever, you can predict reasonably what GDP will be. Or even if you cannot predict precisely, which nobody can really do in statistics. Again, Andrew, everything I say is statistically, okay, constant,
Yeah.
and it's statistical. Okay.
In the beginning of the semester, I was a little confused about that point, but now
Yes.
it's pretty apparent.
Yes, but thank you for making it precise statistically now. So if the GDP of the United States is stationary, then if we take GDP from 1900 to 2020, that we have the number, and then we measure the average and the volatility, and then we add 100 more years of GDP. We keep adding GDP in the future, and we consider the big numbers. The average of those numbers will still be the same as this shorter distribution. The volatility will be the same. In other words, if the GDP is bell-shaped, if it's normal, if it's normally distributed, the same shape will be the same shape if you, no matter how much data, how many more GDPs you add. Essentially, what I'm saying is that GDP in the United States will be mean reverting. Does anyone know what I mean by mean reverting?
Yeah.
Okay. It always goes back to that mean, correct? So in other words, if 10 years ago there was recession. Actually, you remember in 2008, there was the financial crisis, yes? So during the financial crisis, what was GDP of United States? It sucked, it went down. But Andrew, if you were what's his name now? If you were the Powell, yes, whoever was the president if you were the SEC, I'm sorry, the Federal Reserve,
chairman,
the Fed chair at that time, you won't panic, because now at the end of 2008, you say, oh my God, we're in a recession because the GDP of US has fallen by 70%, for example. Now, as Fed chairman, if you know that the GDP of United States is stationary, what would be your prediction? That GDP will keep falling, or that it will turn around and come up?
It will turn around and come up.
It will turn around and come up, because in 2008, it has fallen below its average. And as GDP is mean reverting because it is stationary, you know that it will curve back up. But when will it curve back up? Now depends on you, Andrew, the Fed chair. Because you can quicken that process, or you can delay that process. So I call people like Andrew policymakers. So policymakers, and that's why, if you go to China, Central Bank of China, Fed of US, the European Central Bank, no group of institutions hires more PhDs. in economics, in finance, in mathematics, in nuclear physics, because forever, they are forever studying the distributions of all these policy variables, macro variables. Because if Andrew, if you are the Fed chair and okay, there's a recession, good. GDP in the US is mean reverting, so I know it will come up. Now, how quickly do we want it to come up? We are very lucky in the United States because we have crazy
currency.
we have crazy PhDs and crazy statisticians. So they've studied it. They know exactly if we do this today, it will take 3 months to turn it around. If we do this today, it will take 6 months. So by policy, the government will say, when do we want this to turn around? Okay, the president of US, Donald Trump, or Obama, or Biden, whoever is the president, will say, hey, Powell, turn this damn thing around quickly. And then Andrew will say, okay. Andrew will call his group, and then they will know exactly what to do to turn it around in 3 months or 6 months, give or take, okay? So that's why stationarity is very important. Now, let me ask you then, if the GDP of the United States is not stationary, somebody talk to me. What do you think can happen if it's not stationary?
Anything could happen.
You can't predict it.
Anything can happen, even if Fed Chair Andrew wants to turn it around. It's like, Fed Chair, go do some exercise because stop wasting your time. Now, again, everybody, please listen carefully. If GDP of United States is not if it's stationary, then we know what that means. If it's not stationary, then what is the nature of that non-stationarity? Oh my God, that's the ultimate question. Because the nature of that non-stationarity could be mild, in which case, even though it's not, we want it to be stationary. So therefore, if GDP falls, we can turn it around, mean revert, revert it back to the mean using policy instruments. But if it's not stationary, the non-stationarity might not be too bad, okay? It might not revert to the mean sharply like stationary models would do, but at least it's not crazy. You understand what I'm saying? It's not that crazy. Do you get what I'm saying?
Professor, if it's not stationary, it's heteroscedastic, right?
No. Heteroscedastic. Okay. I get your point. If it's not stationary, yes. Because if it is stationary, it's homoscedastic. Thank you, Danny. All right, you're correct. Okay? Homoscedastic meaning constant variance. Is that what you mean, right? If it is not stationary, then the variance is changing. Is that correct? That's what you mean?
Yeah.
Okay, so yes, in that sense, it can be heteroscedastic, exactly. And we shall try to capture that in chapter 4 with the Gauch models. So if it's not stationary, the stationarity might not be too bad. Yes, exactly. Ian, exactly. If it's not stationary, maybe if we difference, if we take the IBM numbers, yes, if we take the IBM numbers daily, if we take the GDP numbers annual, year by year, and I subtract, beginning in 1900, I subtract 1900 GDP from 1901 GDP. I note that number. Then 1902 GDP, I subtract it from 1903 GDP. I note the number. In other words, I go through each year GDP. I subtract 1 year from the other one. I have just differenced it. Are you with me? I have just created another set of numbers for GDP, but each of these numbers I got from the original numbers by differencing. Are you guys following me?
Yeah.
Okay, so if GDP, original GDP is not stationary, but if I difference the GDP numbers themselves and I get a new set of numbers, and that new set of numbers is stationary, then I say that the original GDP is integrated of order 1. Remember ARIMA, A-R-I-M-A, that I means integrated, right? If I difference it by, if I take the first difference, I subtract year 1 from year 2, I subtract year 2 GDP from year 3, I subtract year 3 from year 4, and I create a new set of numbers. Okay, so some series like GDP can be not stationary, but if you difference them, then they can be stationary. All right. But there is one type of non-stationarity that everybody is afraid of. Can anybody tell me that?
Non-stationarity?
There's one kind, exactly. If GDP follows a random walk process, oh my God, it's like just, you know. Yes, Andrew, yes, I'm just pass you, of course. Of course I pass you, but how do I pass you, with B+ or C- or C+? Or okay, with A+, okay? Now, if GDP of United States is random walk, then all bets are off. Okay? All bets are off. So if GDP of US is stationary, then it can revert to the mean. If it goes down, it can come up. If it goes up too much, it can come down. Okay? It's always reverting to the mean. But if GDP follows a random walk, then all bets are off. What do I mean by all bets are off? If there's a recession and GDP is falling, how bad can it be? Oh my God, it can crash totally. No matter what you do as a policymaker, it can crash completely. If GDP follows a random walk and GDP and the economy begins to boom, good things begin to happen. How good can it be? Well, all of us can get drunk in the street and GDP is still going up. The inflation will be out of this world. It will never stop to come down because it's not mean reverting. Are you guys with me? Okay, good.
Yes.
Thank you, William. Again, I'm not like Andrew, I'm not like Danny, I'm not like William, I'm not like Roxanne, I'm not like those crazy statisticians I have in this class. I am a normal human being, okay? Now, for us all normal human beings in this class, including all those people I mentioned, now come with me now, okay? Let me explain it in another way, because I do research in one way and I'm always thinking of this, especially when I deal with macro variables. Does anyone know what a swimming pool is? Of course, you know what a swimming pool is. Suppose I tell you all, hey, this class, at the end of May, when all of you have graduated with colors and we have all, you know, no more pandemic, you go to Barclays Center, hey, you know, you get your certificate. But I love this class so much, I want to give everybody a treat. So I'm going to invite all of you to a resort upstate New York, where all of us can spend the weekend, bring your families, bring your friends, and it's all on me, okay? But that place has a big swimming pool. So bring your, you know, swimming outfit and so on and so forth. Okay. So we all gather. I already wrote the check and for the place, and you bring your families and friends, and we all, you know, spend the weekend there. But early in the morning, so we all arrive on a Friday evening and have dinner and congratulate. Then on Saturday morning, everybody is asleep. Maybe some people have some champagne and everybody is sleeping late. You know, the whole resort is quiet. And Roxolana, Danny, Andrew, all these my troublemaker friends in this class, you all wake up in the morning because you want to enjoy the morning fresh air. But all of us find ourselves around the swimming pool, okay? Are you with me so far? Yes?
Yes, yes.
Okay, so we're all around the swimming pool early in the morning on Saturday. What a beautiful morning, everything is so serene and calm. And we look at that swimming pool. It's a big pool, Olympic size. And the water is dead at equilibrium. Is everybody with me? It is dead at equilibrium, meaning no single ripple. Okay, so far?
Yeah.
And my man Alex says, you know what? This is too peaceful. Let me shake things up. So what does Alex do? Alex takes a piece of rock, like the size of this cell phone. Okay, so here's my cell phone. So my cell phone is in this case, just this size, okay? And in the quiet of the morning, what does my buddy troublemaker Alex do? He raises it up on the water and lets go. Plop into the swimming pool. What do you think the water will look like? I know, not Alex. What do you think the water will look like?
There's gonna be a ripple everywhere.
There'll be a
bouncing
ripple
off the walls and stuff.
Exactly, there'll be a ripple. But if Alex does it so silently that the thing just goes down at one spot, and if we all begin to look, you will see the ripple begin from that spot. You're in agreement with me? The ripple will begin from that, and you will just see the ripple expanding. You see that expanding. Everybody sees that, right? Expanding, expanding. And eventually, if the water is so calm, eventually it will dissipate. Those ripples will dissipate. And what happens to the swimming pool? It comes back to equilibrium. Are you with me so far? Yes?
Yeah.
Yes.
If that happens, you can think of that as a stationary process. Okay, and then Alex makes more ripples. No, we handcuff him on the chair and say, Alex, stop messing up with our serene morning. So if Alex just drops it like that, bam, like that, and the water ripples, but it ripples, it expands, and then eventually all the ripples begin to settle down. And 5 minutes later, if somebody else comes, they wouldn't know that Alex dropped that thing. That's mean reversion. The swimming pool was perturbed, was shaken by a recession, by Alex dropping that thing. It was Alex shook up that swimming pool that was at peace before. Alex shook it up, but no sweat. It went back. We handcuffed Alex to the chair, to the bench next door. But troublemaker Alex found something, another rock on the ground, and kicked it into the pool and shook it up big time, even now. All right? Yeah, out of infamy. He shook it up big time. And the water, blah, blah, blah. Alex, what have you done? But so big ripples. But okay, this time it took 15 minutes. But guess what? Calm again. Think of that as stationarity. But if that swimming pool, you guys are cracking me up. If that swimming pool was a random walk, and Alex took that little, the first one he did carefully. You are with me? So all of us gather early in the morning, and the thing was peaceful, but it's a random walk type swimming pool. And Alex took that first one and he dropped it. Guess what? Me, I will not be there. Because you see that little ripple that starts, it will become the most violent tsunami. It will swallow all of us. It will, yes, exactly. It will be a tsunami. It will not stop until all the water in that swimming pool has been pushed out and swallows all of us and goes around the whole resort, swallows everybody. That is what a random walk can do. It never goes back. It will never go back to its peacefulness before. All because of Alex. Andrew, will you quit? All because of Alex, yeah? All right, so in fact, if Alex took not this big thing, but this little, you see this little candy I have, this little thing, and dropped it silently into the swimming pool, no matter. If it's a random walk, it will still blow up. Okay, it might take a little longer to blow up, but it will churn, and it will keep churning. All the water will be spouting out, of the pool, and it will not stop until all that pool is empty of water. Do you guys understand? So when we want to test for stationarity in econometrics, in time series, when we want to test for stationarity, really the non-stationarity we're testing for is whether our series is unit root. It's a random walk. Okay? Now, if you all have followed me so far, then I want to show you it's something I typed out, okay, on a little page. But does everybody understand me? Because a random walk process for a macro variable is trouble for us. We want to know if it's random walk or not, because if it's random walk, then we want to know how we can, kind of try to prevent it from getting into trouble, or what to do to the series, and so on and so forth. But the first thing we want to test, if we want to test for stationarity, we can say if it's not stationary, then it can be, if it is not stationary, it can be different kinds of non-stationary. But the one that really concerns us is random walk.
Professor, if it's a random walk, why don't people just leave the asset?
Well, why? I mean,
you know what I'm saying?
If there's an opportunity to make money.
Oh yeah, I mean volatility, but
yes, if there's an opportunity, yeah. The fact that it's a random walk doesn't mean that you cannot handle it, but you need to know whether it is a random walk, so you know the approach to invest or the approach to handle it if you're a policymaker.
Okay.
Professor?
Yeah, I was asking that because you seem very scared and skeptical.
I'm scared. I'm scared, but
of that tsunami, right?
Yes, I'm scared about the tsunami, but I would rather know that it's a tsunami than not know.
Okay.
Okay.
So you could swim through tsunami. I
can swim through tsunami, or at least I go to the highest point of the result and wait for it, and then survive it, right? And then after that, everybody is washed away by the water. I'm the only person around. Then I buy the whole result. It now belongs to me because I knew, and you guys didn't know. You get washed away.
Professor?
Alec, yes.
So what's the difference between random walk and white noise?
Okay, thank you for that question. So I'm going to show you guys now, okay? And stop me anytime to have, if you have questions. Alec, you're such a troublemaker. Your classmates think you're such a troublemaker. All right, let's see.
So funny.
Give me 1 second. Okay, right here. Okay, this is the same piece of paper I showed you last class when we were discussing, remember when we were discussing information criteria. So I discussed this on Tuesday. Today, I go to the next page. Okay. So before, let me just, by definition, let me bring us all up to date with that definition that we know already. So this is an AR1 model, the first one, okay, AR1 model. And it says that x of t is equal to 0.6 x of t minus 1 plus ut, where ut is a white noise, okay? It's a white noise error process. So this is an AR1. Now, this AR1 model does not have a constant before it, right? This is a zero mean AR1. Everybody understands why, yes?
Because it doesn't have the
constant.
P0 is 0.
Exactly.
Yeah.
Okay. So it's a pure AR1 with zero mean. But in the second equation, I introduced mu. I introduced the 4.3. Yes. So in the language, in the time series language in financial econometrics, we say this is an AR1 with drift. In other words, it's a 4.3 mean So the average here, the constant is 4.3. It's a 4.3 average AR1 process.
Professor,
But
is
yes.
it possible you could show us these with graphs, and so it's more stimulating, I guess?
Okay, I will.
Next
okay.
class, yeah.
No. Even tonight. Okay, maybe next class. Tonight, I seem to be running out of time, but yeah, I'll do that next. I have it. Okay, I have it. So I'll show you. I just want to explain intuition.
Yeah, because
first.
in my head, I'm imagining like a sine wave, and then something like that.
Okay, yes, you can do that, but I'll show you next class. Okay. Okay. Tonight, I just want to give definitions. Okay. So this is an AR1 with drift. That's the language we use. But here, how about this third one? It's an AR1 with constant, but then I also introduce a trend. You see?
Yes.
So as time goes on, month by month, year by year, this time series also, there's a trend over time. Remember, if it's a zero mean, then everything fluctuates around zero. If it's a 4.3 mean, it's it's not at zero, it fluctuates around 4.3. Remember, when you guys download your data from Yahoo, and then you calculate the simple rate, and if you bring your data prices, adjusted close price, and you plot the time series, remember that's a trend, yes? That's the time trend on the price. But when you convert it to return, you subtract and then divide by the original, then what do you see? You see it's fluctuating, but around zero mean. Yes, everybody, you've done that for homework.
Yes.
Okay, but if the mean is 4.3, instead of fluctuating around zero, it will be fluctuating around 4.3. Okay, not zero, around zero, but 4.3, so around 4.3. But if you now introduce a time trend, it will not just fluctuate around, but it will be trending up. It will be trending up. So that we say that model is an AR1 with drift and deterministic trend. Deterministic says if you give me the time 2 months, I multiply by 0.35. If you give me 10 months, I multiply by 0.35. So the amount by which it is growing, I know it is deterministic. It is predictable. But instead of this 0.35, if I write 0.35 squared divided by square root of pi, then parentheses times t, then it's no longer deterministic. Well, pi is still constant, but if I put a little epsilon there, then it's no longer deterministic, it's stochastic. Then I'll say this is an AR1 with drift and stochastic trend. But this one here is AR1 with drift. What is the drift? This 4.3. And what is the deterministic trend? This 0.35 times t. So these are all AR1 models. AR1 model with zero drift, the first one. AR1 model with 4.3 average. So in other words, it's fluctuation around 4.3, up and down, up and down. But this is AR1 with drift and trend. It's fluctuating around, but it's trending up gradually. Okay. Okay. Now, what is random walk? Look at this one. This one is random walk. Compare this random walk with the AR1 model. What is the difference? What is the difference between this random walk, the first one?
Doesn't have a coefficient in front of the xt minus 1.
Actually, you can do better than that. What is the coefficient?
It's 1.
Coefficient is 1, exactly. Thank you. Okay, so a random walk is like an AR1 model with coefficient 1.0. 1 exactly. That's a random walk. And
so that means that it doesn't have a mean, right? Because it's phi 0 over 1 minus phi 1.
Yes,
and if that's 1.
Yes, in this case, there's no constant, there's no mean here. I didn't introduce it. But in this second one, I introduced a mean of 4.3, yes? So this is a random walk with drift. It's a random walk because the coefficient of the xt minus 1 is 1.0. And the third one is a random walk because the coefficient is 1, but it has drift. It also has deterministic trend. So this is random walk with drift and with deterministic trend. All of this you can see on the graph. And who asked me that was Andrew or Alex? I'll bring the graph next week, okay? I'll show you. Pure random walk with no drift, random walk with drift, random walk with drift, and deterministic trend. I just have to look. It's all over the place, okay? I have actually the one with drift. That's the one I think, okay. But so when we want to test for whether our series is non-stationary, generally, the tests that you see in statistical packages like R or Stata or Oxmetrics or SAS or SPSS, those packages, they want for you to first specify what kind of random walk are you thinking of. So you have IBM series. You want to test whether IBM series follows a random walk, whether IBM series is stationary or not. But if it is not stationary, the kind of non-stationarity we really want to see whether it's present is a random walk. Okay, everybody with me so far? So guys, everybody please listen carefully because you will see this terminology over and over. If I tell you that this is, that this first equation, the random walk, has unit root, what do I mean? This coefficient here is 1. Okay? Technically, that's not really what it means, but for me to describe what unit root is for you, I have to bring, you know, a circle with all kinds of complex roots. I won't go into all that. Just when we want to test whether a model, an equation, or a series has random walk, we're essentially testing whether the coefficient is 1. That's just keeping it simple, okay? Statistically, it's just a headache for me to describe. I have to prove so many things for you. And you know, I can refer you to. But if we want to, so Danny or Alec, whoever give me the answer, simply because this coefficient is not 0.6, it's not 0.8, it's 1.0. So if I want to test whether this is random walk, I'm testing the null hypothesis, is the coefficient equal to 1? As opposed to, is the coefficient not 1? But really, if we want to say test for stationarity versus non-stationarity, for this to be stationary, for this AR1 to be stationary, what value must this coefficient take? Remember, we discussed it in class.
Greater than 0.
Anything that's between -1 and 1.
So the absolute value of the coefficient has to be less than 1, yes?
Yes.
Exactly. So to test whether this is a random walk or not, we say null hypothesis, HO, it's random walk, versus alternative, it is stationary. And by stationary, we mean null hypothesis, the coefficient is equal to 1 exactly. Alternative hypothesis, the coefficient, the absolute value of the coefficient is less than 1. Because if it's less than 1, then it is stationary. You guys with me? All right. There's silence in my class. Are you guys following me? Everybody? Roxolana? Lily, you haven't talked to me today.
Yes, I'm following.
Okay, excellent. Very nice. And everybody else. Joseph Joe, are you here? Are you listening to me? Is Joseph Joe here today? Okay, it's past midnight over there where you are. Actually, it's almost 7 a.m. So, all right. And those of you in China, I mean, you better be sleeping by now. It's early 7 a.m. there now. Okay. So when we want to test for stationarity, there are different tests. There are different kinds of tests. And that program, that software R does a good job depending on what package you are using, okay? So when we begin to use R to test all of this, then we shall see exactly what the numbers say. Okay. So typically in R, when we use the packages, there are different kinds of tests to see whether a series is stationary or not. Okay, and those generally we are testing for unit root non-stationarity. That's just fancy word to say we are testing to see if the time series follows a random walk. Because unit root, meaning, again, in the simplest language, that the coefficient here is 1. Unit root non-stationarity. If the coefficient is 1, just like in this situation, it's a random walk. But if it's a random walk, it can be a straight random walk with no drift and no trend, or it can be a random walk with drift, or it can be a random walk with drift and deterministic trend, and so on and so forth. Okay? So I want to introduce us to the different kinds of tests we can see in R. So in general, these are the 4 different kinds of tests. And some packages, some packages in R, when we want to do the test, it will have a default test. You remember how for homework 2, you guys did measures of linear dependence, and you had to specify whether you're doing Pearson or whether you're doing, what are the other 2, Pearson or Spearman, and so on and so forth. And you have to put it in quotes, all right? So if you want to test for unit root non-stationarity, in other words, you want to test whether your series follows a random walk, and you don't specify any test. Many packages will choose one of these 4 as default. And typically the one they choose as default is this one we call ADF. But if you want a specific one, you can ask it for DF, or you can ask it for ADF, or you can ask it for PP, or you can ask it for KPSS. And this KPSS tests for all these 3 combined: random walk with drift and deterministic trend. So what is the DF? The DF is called by 2 professors, Dickey, D-I-C-K-E-Y, Dickey, Fuller, F-U-L-L-E-R. I think Professor Fuller used to be a professor of statistics at the University of Washington, somewhere, I forget, but that's a long time ago. And this one is by the same 2 professors, but they did something, they augmented it, and I'll explain what augmentation is next week. Augmented, Dickey, Fuller. Okay? And the third one is, sorry, I had too many equal signs. And the third one is Philip Perron test. You will see all of this when we begin to do the R. And this one will be, oh, this one is long. K-W-I-A-T, Kowski, Kwiatkowski, Philip, yeah. Philip Schmidt, and Shin, S-H-I-N. So the KPSS is Kwiatkowski, Philip, Schmidt, and Shin. Those are the 4 people that, the same Philip here. Those are the 4 people that introduced this test to us, okay? So any of these tests we can use to test for unit root. And whenever I say unit root, you can think of it as unit root, meaning I'm testing for random walk, because I'm testing if the coefficient is 1.0. So in your textbook, I think it's on page, unit root, I think it's on page like 93 or something like that. So or 86 or 18, something. It discusses unit root. When we're testing for unit root, we're testing for random walk, okay? All right, so we can test for either straight random walk or random walk with drift or random walk with drift and deterministic trend. So all these 4 tests, we'll be talking about them in R, okay? Next Tuesday or so, I will maybe bring a package and run the test. Or I can actually use the one in the textbook. I can go by the example in the textbook and then maybe use other packages. So testing for stationarity is not that straightforward, because again, each of these ones, and I'll ask you to keep track of them, each of these tests has its own HO and HA. These first two, the DF and the ADF, if I remember correctly, the null hypothesis is that of unit root. That is, HO, our series follows a random walk. And HA, our series is stationary. So these first two, I'm kind of sure, because I use them quite regularly. All right. But the other two, I think another one is the reverse, meaning the null hypothesis is that the series is stationary versus it is non-stationary to the unit root type. But I will check, we'll see all of this on R, okay? But I'll keep reminding you that no matter what test you use, just like we did in previous homework assignment, no matter what test we use, you always have to keep up with what does the null hypothesis say and what does the alternative hypothesis say. Okay, guys? All right, so does anybody have a question? I'm going to stop recording now, and then we can take last minute questions.
That would go along with the conclusion, right? Like, say if it is a cube or unit root,
yes,
then this unit root is random walk.
Yes.
Okay.
And then because again, we shall see next class, this Dickey-Fuller test and many of these tests, you cannot use the ordinary T statistics that you use in Echo 4000 or in your statistics class, because of the nature of the random walk. These guys, Professors Dickey and Fuller, they derive their own T statistics, their own critical T. So each package will give you a p-value based on their own T statistic. And in many packages, they actually, if they give you the T, the sample T, they actually give you the list of the critical T's for 5%, 1%, 10%. They give it to you right there in the package. So this is a little bit complicated, but we shall see in R that once you do the test, and if the null hypothesis is that of unit root, that means random walk, and against alternative that is stationary, if the p-value is less than 0.05, then we reject the null and say we reject the random walk in favor of the fact it is not random walk, it is stationary, okay? So we shall see all of this when we begin to do the R session, okay? All right. So I'm going to stop recording now.
The recording has stopped.
All right. Okay, guys, I'm sorry I kept you a few minutes beyond, but I just wanted you to get the big picture. So next Tuesday, I plan to maybe do a short R session on what we discussed this week. And then when I'm done, I'll introduce us to the moving average models, the MA. Remember, so far we have been talking about the AR models. So we talked about the AR, we talked about the characteristics of the AR, the mean, the variance, the auto-covariance, and autocorrelation. For AR models, how do we determine the autocorrelation at each lag? take the coefficient 0.6 or 0.8 of the xt minus 1 variable and square it if you're looking for the auto correlation at lag 2. If you're looking for the auto correlation at lag 5, take that 0.8, raise it to power 5. So we derived all of this for AR models. For MA models, when I introduce them to you next week, I will not derive the same thing. I'll just say the autocorrelation at lag 1 this is the equation. The autocorrelation at lag 5, this is the equation, okay? I won't derive anymore because you know we can derive, but these are the answers. So I'll introduce the moving average models for us. I'll give you the equation for their mean, give you the equation for their variance, give you the equation for their autocovariance and autocorrelation, and you just have to accept it from me. And I'll point out to you in the textbook. If you want to see the proof, you go there. But I won't prove it in class like I did with AR, okay? So next week, I'll introduce characteristics of MA, give it to you, and then we move on to ARMA. But whatever we do for MA, then we can test for stationarity. We can do all those tests, you know, a portmanteau test. We can do all those things we have done so far. So I don't need to repeat them anymore, okay? All right. Have a nice evening, everybody.